Hello and welcome back to another machine learning series. This time I want to discuss a pretty unusual model. Okay, usually a supervised learning algorithm need a ton of training dataset to produce a good prediction or classification. The model we talk about only need a few training data per class. We talk about 8, 10 or 20. Furthermore, with only this dataset, the model can do a good classification task in the case of dozen class. We talk about 20 or 40 or anything. Anyway, in case you confused about what class I mean in this video, I will explain it first. Okay, suppose you want to predict weather using a machine learning model. The possible weather are sunny, cloudy, rainy, and snowy, which means there are 4 classes for that case. A model which can do this feat is called one-shot learning. One of the popular one-shot learning models is Siamese neural network. It is the general structure of Siamese neural network. Unlike vanilla neural network, the input is two separate row or item, since we will try to compare these two items. This item can be anything, but in most cases, we use image. Since we use image as an input, the feature extractor will be some convolutional layer. Like its name, the point of this section is to transform those two items into a vector. The network for the feature extractor for item 1 and 2 is the same. There's no clear rule on how to design the feature extractor. You can just trial and error to find the best structure, or you can just adopt the backbone of any successful pre-trained model. Adopting a pre-trained model can be best choice because those models are already proven to be good feature extractor, since their accuracy is good for their case. Now some of you may be asked, what is the backbone I mentioned earlier? So basically, any model, especially deep learning, consists of backbone and head. In other models, the head can be further divided into neck and head. Backbone basically is a feature extractor. In the CNN model, backbone part is the sequence of the convolutional layer, pooling, and others until we get a single vector. The head is the processor or computation unit for that vector to produce a prediction or classification. This computation can only be done using a dense layer, especially in the output layer. You know, the total neuron in the output layer is the same as the total class. Now, for the distance operation, this becomes part of dense layer or separated operation. If this is a part of dense layer, then we can concatenate the feature of item 1 and 2 into a single vector. If we decide this is a separate operation, we can do any mathematical operation. Some people do multiplication and some people do subtraction. In my opinion, this is trivial because the dense layer ahead can adapt to any input thrown at them. The dense layer can be any depth like feature extractor. This dense layer actually is the head of the model. The dense layer consists of some vanilla neural network layer, some regularization operation like drop layer, and some additional operation that believe can be improve model performance or avoid vanishing or exploding gradient like batch normalization. Finally, at the end of the layer, we will decide if these two items belong in the same class or not. Usually, we will do a sigmoid operation in this step. So after the dense layer output a single value using linear operation, we feed it to the sigmoid to get the probability value. And that's all how the model fit our input and produce a prediction. At least, that is how the code I find work. In the other article I found on the internet, they are treating the output of the feature extractor like a real physics vector. Hence, the name of the part after the feature extractor is distance operation. So if we plot the feature from feature extractor in scatter plot, if these two items belong to the same class, then their distance must be close, otherwise it must be far. That's why we can just fit the distance value directly to the sigmoid to get the probability value. But I think their difference is not important. Remember, this is a neural network. It can decide what part is important when what is not from the feature extractor and can do an approach of simulation any mathematical operation if it wants. So adding a dense layer or not at the head of the model is both okay. To calculate the error, we can use any normal loss calculation method. using slight binary cross entropy, but there's a popular choice use a triplet loss where we compare three images, anchor, positive, and negative, to make more clearer for the model to differentiate the anchor and positive item, which is belong to the same class, and against any other class or even unclassified class. To do this, we must use a triplet feature extractor instead of twin, since we input three images. But remember, this feature extractor actually a single feature extractor that run twice or triple time. Now we already covered some general and basic theory. Let's go to the hands-on section. On my first slide, I try to make the model to learn to differentiate myself and some random K-pop idol. So I try to Google them and put them in the dataset folder. I also take some selfie of myself and put them in the dataset folder. I'm using the CMS code from user sohype023. In this code, we use a pre-trained model for the feature extractor and some dense layer together with some additional operation like batch normalization and drop layer. Now, let's train the model. This is our first try. So here I already prepared the data for training. Here I have 6 selfies, and for the random K-pop idol I choose this 6 photo, and then let's run this using this train data. And okay, now let's try the model, and to use the model, let's look the repository. So to use that, I must do this train path. I forgot the script. And the duration is literally 1000. Yeah, I think we need to wait. Okay, see you in the next section. Okay, now it's done. Let's validate, or let's check the accuracy of our model. And to do that, we must do this. Python evolve.py is fall, min o is less, and min c is, let's see, we will use the best.pth. Let's see. And as you can see, our accuracy is just 25%. This is very bad. Let's look the result. And yeah, this is right. This is not me. And this is basically the same photo, but the confidence is very low. It's just 30. And yeah, this is basically the same person, but confidence is also low. This is me, but the confidence is low too. So yeah, as you can see, our first experiment is failed. I wonder what is the cause of this. The result is not good. There are two possibilities. One is the model structure is not good enough, or there's something with the dataset. In the GitHub repo, the author show how good the performance of his model is. I also tried using an omniglot dataset, which I think is a toy test dataset for CMS neural network. The result is good. I think there's nothing wrong with the code. On my third try, I'm using the face dataset from Kaggle. There is 40 face or class here. I'm quite skeptical now because in my previous experiment, when I only used 2 class, the result is not too good. How come the result can be good if I try using 40 class? Okay, now let's try the 40 face dataset. I already trained this model, so now we just do the evaluation part. I forget the parameter for the script, so I want to know. Okay, now let's run. Wow, the result is good. The accuracy is 90%. Let's see. And this is the plot. As you can see here, same person, the confidence is 72. This is different person, the confidence is only 15. Same person, same person, same person. And here, as you can see, for different people, its confidence will be low. But for the same people like this, the confidence is high. Yeah. Now, so the summary is, the result is quite good for me. This is quite plot twist. Now, I'm trying to find the difference between my dataset and this successful dataset. Looks like in the 40 face dataset, the entire image is a full face without any other body part or anything. Okay, now on the fourth try, I'm still using my selfies, but instead of using random K-pop boy band face, I'm using my brother photo. I cropped both photo to the face and then retrain the model. Now let's try our last experiment. I already do the training part. Now we just do the evaluation part. The result is, the accuracy is 89. This is good, right? And this is the plot. Looks like for my face, the confidence is same because yeah, this is the same person. And for me and my brother, the confidence will be low. And this is right. My face, the confidence higher than 50. Yeah, right, 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 right. And for this is wrong because this is literally two different person, but the confidence is more than 50. Like, this is also wrong. Right, wrong. Hey, no, this is right. This is right, right. So yeah, from this from this 18 plot, there's only 2 wrong and the rest is right. And I think this is the good result. The result is quite good, but I think can be improved. Now, if you want to implement this model operationally, you can just choose one photo from the dataset as one of the input for the model. The rest is the photo you want to test. But before being fit to the model, we need to crop the face, and this is bothersome. But if you watch closely at your smartphone camera, there's already an existing algorithm to detect face, right? What you do is just get that bounding box and crop the face automatically. I will show you how to do it, and we will build a working smartphone application using this Siamese neural network next time. Until then, see you in the next video. Bye.